calorimetry problem involving a phase change. So we got everything set up here. This little blob up here represents our steam. So we have steam being added to water that's being held in an aluminum cup. And the question is, how much steam, we're solving for the mass of steam required to change the temperature of the cup and the water from 20 degrees Celsius to 50 degrees Celsius. And one thing you got to realize is that all three objects, the steam, the water, and the aluminum cup, all three objects are ending at the same temperature, which we call the equilibrium temperature. So everything ends right here. Okay? So the trickiest part is realizing that the steam goes through 3 steps to get to the final temperature. So that they tell us the steam starts up here. This is 120 degrees Celsius. The steam starts at 120. And to get to the equilibrium temperature, the steam goes boom, which is cooling. The steam first cools, then the steam has to condense to a liquid, and then the steam cools again, right? So it's got to go through 3 steps. Now, the cup and the water, hey, we close that back door. Please. The cup and the water have to go through 1 step. All the cup and the water have to do, the cup and the water just go up like that, okay? And the delta T, we know what the delta T is for that step. So the starting temp for the cup and the water is 20, the ending is 50, so the delta T for the water is going to be what? From 20 to 50 is what? 30. That's the change in temperature for the water, and then same thing for the cup. The delta T is going to be 30. Okay? Now, what's the delta T for the steam up here? Right here. What's going to be the delta T for that step? The delta T for that step is, so from 120, the starting temperature is 120, and then right here is 100, so what's the delta T? From 120 down to 20, I'm sorry, from 120 down to 100 is what? 20. Well, technically it's negative 20 because it's cooling. Negative 20 degrees Celsius. And then what's the delta T for this step, for the steam? The delta T for that step is from 100, it starts here at 100, and then that's 50. So what's the delta T for that step? Negative 50. Okay? Oh, and one thing you got to realize is the specific heat for steam is not the same as the specific heat for water. Steam and liquid water have different specific heats. And I'm going to give you specific heats. You don't have to memorize them. They'll be given. And then the final thing you got to know here, so the equations that you're using, Q equals ML, and then Q equals MC delta T. All right, so when do we use Q equals MC delta T? You use it on wherever there's a temperature change, right? Wherever there's a temperature change, you have Q equals MC delta T. When do you use Q equals ML? That's for phase change, okay? So let me try to clean this up. Okay. Oh, and we have to have the L, the latent heat of vaporization. The latent heat of vaporization for water is 2,260,000 joules per kilogram. That's the L. If you're up here, it's called latent heat of vaporization. If you're down here, it's called the latent heat of fusion. All right, so I'm going to erase the problem so we have some room to solve this. So I'm going to set it up and then let you guys do the algebra. But the setup looks like this. The main idea, so big picture for these problems, what's the big picture? Heat loss must equal heat gain. So which objects are gaining heat? The objects that gain heat are the aluminum and the cup. So we got to turn this into an equation. Huh? the water and the cup are gaining heat. The steam is losing heat. So basically it's this. It's heat loss. How are we going to say? Heat loss equals heat gain. So negative Q equals positive Q, right? Heat loss equals heat gain. But we got to think about this. So let's deal with heat loss first. Let's do heat loss. So the object losing the heat is the steam, but the steam is losing heat in 3 steps. 1, 2, 3. It's 3 steps. So let's deal with this first step. What's the equation for this first step right here? M, C, and then let's just put in the delta T. What's the delta T for that step? 20. Let's just put it in. Okay? And then that's going to be specific heat of steam. So S for steam, and then M1, this will be M1, this will be M2, this will be M3. So M1, 1 is steam, 2 is water, 3 is the aluminum. So we go M1, specific heat of steam, times 20, that's MC delta T. Okay, second step. What's the equation for that second step? ML, so that's going to be M1 times the latent heat of vaporization, which is this 2,260,000. That's the latent heat of vaporization. Okay, plus this third step here. That's going to be MC delta T again. So that's going to be M1 specific heat of water, because look, the steam is now water. It's become water. So, and then the delta T is 50, right? Now, look, technically these are all negative, right, because it's losing heat. The thing I told you to do is make this absolute valued. You're just going to go absolute value of heat loss equals absolute value of heat gain. You can do that unless they're asking for the equilibrium temperature. If they're asking for the equilibrium temperature, then you have to include the negative. Okay? All right. So that's all absolute valued. Okay? So now this is going to equal, now, cup and water. So let's do the cup first. The cup, this is easy. It just goes one step. That's going to be mass of cup, which is M3, specific heat of the cup, which is aluminum, specific heat of aluminum, and then what's the delta T? 30, right? It's going from 20 to 50 times 30. Then plus the water, that's going to be M2, specific heat of water. Make some room, get this out of the way, and 30. Now, if you look at this equation, that's a 30. If you look at this equation, the only thing we don't know is what? M1. Solve this for M1, and you're going to get 0.0207, which the book says, the answer, if you look in the book, they convert that to 21 grams. Just round that to 21 grams, which is the answer. Heat loss equals heat gain, but the steam goes through 3 steps.